Right, well, any questions or comments on that one?
John, what does your theory say about the braiding of quasiparticles in quantum Hall?
Not a lot, not a lot, Lou. I am relying on you to take things in that kind of direction, and on some future conversations to be had. This is pretty much where my knowledge. I'm only proposing here really the theoretical basis of what these things look like. When I start looking at how those things fit together, not a lot. But having said that, I know nothing about it. I'm going to answer the question anyway, of course. But modulo the fact that I think what's happening is that what you have is as you go into the fractional quantum Hall regime, that you have systems which are resonant and harmonic at odd numbers so you have a triple threading, for example, of magnetic flux quanta through a single electron, that kind of thing. But what you also have is the system is not, okay, let's go back to the integer quantum Hall system, where what you have, or the superconducting system, where what you have is you have a set of identical bosons. This object is not a bunch of di-electrons in a superconductor because they're all identical. It's like a single macroscopic quantum state of things where there is an ordering through the entire system, going across, going front to back, and going up and down, of these things all flowing through one another as bosons, as in a laser. And what I'm envisaging is one beautiful three-dimensional braid which goes through these things. However, what I think would be very interesting to experiment on was making the system smaller. So you take your superconductor and you start chopping it down until you end up with something which is just pretty much linear. Then you should just have the snaky thing going through that direction. Then you could say, okay, well, we'll take it and now we'll do it big in 2 dimensions and small in the other one. And then investigate those sizes. You should get changes in the critical current, in the critical transition temperature and so forth as you do that. But I think there's an immense amount of fun to be had here, because you can also do a superconducting ring, a very small one, and look at what that does, and then look at the orientation of that with respect to a magnet, because these systems also break down in magnetic fields. I think there's an immense amount of beautiful experiment to be done here and to be played with here, that at the moment, people just don't have any way of thinking about these things. But I'm pretty much convinced that what we're talking about here is we're talking about a single continuous flow going through these things, which has some sort of wave associated with it, like your beautiful braids. I think that's the kind of thing we're going to look at. But as I say, you're way ahead of me.
I hear a lot of beautiful geometry there. I want to focus on the basic question, which is you have a physics happening in a planar space, and you have more or less located quasiparticles, one here, one there, say, and if they go around one another in the plane, you expect a phase change, and the question is, can you understand what phase change you would get?
Yes, one would expect to have a phase change indeed, and yes, one can understand what phase change one would get. So if that phase change is coherent, so it's an Aronoff-Bohm system, if we're talking about a 2-dimensional electron system, and you split the thing into 2 directions, that phase thing is just an Aronoff-Bohm phase. So it's coming from the vector potential, but now a physical vector potential, not a non-physical vector potential, or an arbitrary vector potential, which means that the gauge is fixed for such things. And there's a lot of nonsense talked about gauge freedom and gauge invariance, but no, the actual phase change around such a loop in a 2-dimensional system is well known. It is the enclosed flux, or it's E times A. It's EA. Some other constant in there if we want.
That's at classical level, right?
That's at the classical level, yes.
Yeah, and I think that what we want to know is what happens at quantum level.
Well, that's going to depend on the size of these objects. So if you're doing a rotation around one another, there's going to be an enclosed flux. Now, for the system where you go from a single system, which has one enclosed flux going around exactly once, that's resonant and harmonic. If you now triple the magnetic field, then it's going to go around, it's going to come back on itself with 3 enclosed flux quanta. So those are the sorts of systems and one will then have 3 times the change of phase, either 1 or 3 or 5, or ones where you're going to be in harmony here with something that's a di-boson, a di-fermion. But Lou, the simple answer is I don't know. I'm making this shit up, right? so I'm only just getting into the beginnings of thinking about this sort of thing. So
now I heard you also talking about something really interesting and more complex, which is that you were thinking of one of the electron as like a toroid, and something could go through the middle of it, right?
That's
you have
right.
braiding of that kind. So you have like loops, and loops could braid. Loops can braid around one another externally, or they can go. The loops can loop the loop and go through each other. That's a kind of braiding that people have studied in topology to some extent. That it occurs here would be very amazing.
I think it would be absolutely fantastic. I think you're right. And you can sort of imagine taking something which is low dimensional and then plotting into something which is low dimensional 2D, and then putting it in something which is low dimensional 2D perpendicular to that. Now, wouldn't that be interesting? So I'd love to try and, well, we can propose that kind of experiment. Oh, I should also say to everyone that the central part of that, where I say how the superconductor works, what to do for going to room temperature superconductors, we're not going to post that. That's going to be Quicycle confidential. So that particular bit's going to get taken out of the video, which is going up onto YouTube. So because I think there might be a patent in there, and we need some sources.
But you'll send your slides with or without that.
Without that, yes, I can.
Okay. I want your slideshow for the basics anyway. So
you can have the slideshow with Lou. So don't give it to anyone. So okay,
great.
Thank you. Thanks a lot. There's a lot of food for thought in your talk. You covered such a wide ground, basically so broad. And lots of thoughts cross my mind, but I don't know where to begin to ask you a question, in fact. So
Go for it.
It's an enormous amount of field you're covering. You're covering from a Pauli exclusion principle all the way to di-electron systems, to topological binding, to the EMC effect versus the superconductor, etc., etc. Let me just start with some question, in fact. I just was wondering about certain things. You mentioned that the electron has got 5 times 10 to the power 8 Teslas, whereas the proton nucleons have got a factor of 10 orders of magnitude higher than that. But then if I think simply, because the electron is much smaller in size compared to that of the protons and neutrons, and also much lighter.
No,
it's much thought that
no, it's much bigger, Chari.
But in your model. But the thing is, if I do an experimental electron scattering wise, when we do that, put a GeV, I still see the form factor to be a point like form factor.
You're right.
Take that from.
Look, I'll show you the calculation. Look, here it is. So that's
smaller in size compared to the proton and the neutrons.
No. This is a terrible misconception.
Wait.
Yeah, go on.
Okay.
Yeah, go on.
Okay, if I use that concept and if I take that one, then I have to conclude that it is much smaller in size. It's much smaller. Then I have to think that its magnetic field intensity, if it is something there, it's going to be much higher than that of the protons and the neutrons. But now that is my count. So there are quite a few things. That's one question we had. The other thing I had was.
I'm sorry, I'm being a bit shorter than I think. No, but remember that the what you know is not how big.
You said the topological binding versus the energy binding. Okay, I stay quiet. Okay, go ahead, John.
No, don't, because I'm going to answer you, of course. So okay. The thing is, you're right, the form factor of the electron looks like 10 to the minus 8. You're looking at something which looks like 10 to the minus 18 meters in deep inelastic lepton scattering. But it's a widespread misconception. That means the electron is that size. It's not. It's much bigger than that. What's happening? Your measurement tells you that the electron scattering is scale invariant. Now, a sufficient condition for observing that is that the interaction remains inverse square and that the electron is a single object. You don't need it to be small. You do not need it to be small. This is a misconception. The scattering is point-like. It's not point scattering. It's point-like. And that's a different thing.
Yeah.
And the reason that scales down to infinitely small is that if you have two electrons, which are really rotating photons, coming around into one another, they only see the bits that are moving towards each other. And if you move them forwards faster and faster, they blue shift. So one side, just as in the clock, just as in Garnett's clock, it's blue shifted one way and it's red shifted the other way. But the bits that are moving apart are still moving apart at light speed. You only see the bits that are moving together, and they scale like a photon. And the energy of the interaction scales like the exchange photon. They scale in exactly the same way. So you see no structure. And the form factor remains, it can go infinitely small. So, but the actual electron size is much bigger. Small is, but just from E is h nu, from hc over lambda, the protons 10 to the minus 15 meters, and the electrons 10 to the minus 13, and neither of them are anything like 10 to the minus 18. At 10 to the minus 18 meters, the electric charge would be millions of times the electric charge field mass would be millions of times the electron mass. The things can't be that small. Where it comes from is that the problem is that you read this in books. You get people who don't understand what the difference between point-like and point is, writing the books, telling you the thing's small. In quantum electrodynamics, the thing's taken to be a point particle, so you have the theory which says it's small, but it's just not true. It's just a continuously repeated simplistic ignorance that's spread from people who don't know, and that's everybody, because who the hell does deep inelastic lepton scattering? Everyone's the same. If you don't get your source right, you've already lost it in terms of these things. But no, electrons are much bigger than protons, much bigger. 10 to the minus 13 compared to 10 to the minus 12 compared to 10 to the minus, well, 2,000 times, it's just the mass, or 1,800 and whatever it is times. They're much bigger. Okay, good.
Thank you for also reminding me about Alfred White Northhead, Alfred North Whitehead, when you brought in the process versus the entities.
Yeah.
So interaction versus the process you were talking about. This was the process philosophy of Whitehead back in early 20th century. And I'm always reminded of that. And then now today, again, you brought it back to my memories, in fact. Thank you very much for that.
My pleasure. Thank you. Yeah. More questions?
Yeah, I have one. Can I? Yeah, okay. So I'm very interested in this discussion about crystals two-dimensionality and how that electron actually looks like in 2D. Can you give a vision of how the 2D electron actually looks like? So it has turn, it has twists, and it has some tumble, but not full tumble, right?
Yeah, I think the thing's quite big. So the thing's in a two-dimensional electron gas, the electron is now 40 nanometers in size. So if you think about that, that's a charge distribution. So what you have is you have a very steep binding between, we're talking about an L-gas heterostructure, something like that, a heterostructure material. So it's sharper on one side than it is on the other side. So it's a little bit asymmetric, but nonetheless, it's going to be hard for the tumble to take place. It's going to tend to stop the tumble. And the thing's big, so the moment on this is huge. We can work out the forces if you like, or work out the.
So if we focus on that tumble, that it's constrained to not have as much of when it's in two dimension, when it's squeezed together by a high electric field.
Yeah.
And then in a superconductor, you often talk about the phonon interaction between the planes in the high temperature electron.
Yeah, I know. It's total bullshit.
I think that has to do maybe with the tumble, that you can actually have more tumble when it can interact with the next plane.
No. The problem is that you have the isotope effect in superconductivity, where people look at the superconducting transition temperature as a function of temperature in, I forget what the isotope was again, in a particular, I think it might have been lead, yeah, it was lead, lead isotopes. They looked at different lead isotopes and the transition temperature is different. Now, the only thing that people could think about that could be in the kind of theory that people think about, where you have this fixed lattice, and then you have the electron sitting on top of that, is an electron phonon lattice. But Stanley Rahm used to say that thinking that the phonons were playing a role here was like thinking that if you had a gas explosion in a house, that it was the gas that was holding the house together before it exploded. Of course, the stuff's come out. It's complete nonsense. The problem is there's nothing else there. You've got a mouthful of teeth. You have no you have this effect, and you have to try and find some mechanism by which that could happen. But to have the same thing binding, the phonon binding the thing in the first place, and then have it destroying the superconducting thing, it's schizophrenic. It's because you have no other tool in the box to think about it. I think it's really mostly just nonsense, that whole phonon stuff.
I feel that the nonsense is maybe that you have to have a phonon, but the problem is that you do have phonons.
You do,
and then
right.
those phonons have to be in resonance with what the electron wants to be.
Yes, and when you see that, yes, that is the case, because if you now think about lattice vibrations, so you think about that reentrant superconductivity that I showed around 110 Kelvin, then in that case, what's happening is what the phonons are doing is they're changing the lattice spacing. They're effectively, well, expanding and contracting just by heating and cooling of the system to get it to the right kind of size to be coherent with the system. So, but the coupling isn't direct with phonons as it is in the as it is in the phase transition theory, as it is in the Landau boson, Landau-Ginzburg theory. So, so I mean, I don't know much about this stuff, so I have to say that. Well,
but I think when you talk about it, it's very difficult to break these bosons once they have condensated.
Yeah.
The problem is that you have a lattice, and that's not perfect because you do have phonons.
You're right, and eventually, so I think the only role of phonons is no phonons, absolute zero temperature, superconducting, quite okay, except if the thing doesn't fit. But then what phonons normally do, of course, is, you know, there's a critical temperature at which superconductivity takes place and which it breaks down. So you then lose superconductivity as the phonons begin to hack into. Although I'm saying it's strong, I'm saying it's strong with relation to current theory's strength of superconductors. High temperature superconductors just prove that there's something wrong with this. Well, it's just not right. It's the way science is supposed to work. You do an experiment to test the theory. When the experiment says the theory is wrong, you should throw the theory away. People have stopped doing that. They've got sort of going, oh yeah, well, it's all right. We don't understand this.
Yeah.
We don't understand this too, so it's okay.
I agree that once we open up our minds by thinking about the electrons as confined photons, then you can free up your minds to think about how the phonons also take a play in that interaction between the electrons in a pair.
I think they still are important, but I don't think they're important in binding the superconducting pair as they are in some of the theories.
No, but the problem is that those electrons do exist in a crystal that is not perfect, so it is vibrating, and so it has to have phonons, and those phonons have to have resonances that are in phase, in coherence with the electrons, as it has to want to tumble.
Well, Joakim, that could actually be the mechanism for the resonant stuff in the temperature dependent, but I don't know. I mean, this is going beyond my understanding of how.
Yeah, but I think going to lower dimensions to actually shape a circular or ring shape topology.
Yes, that kind of thing. Yes.
Where you design in the tumble.
You design in the size. So you have a ring-shaped gate. And you
tune the tumbles, like you tune the tumbles to be in coherence with the phonons.
Exactly. Yeah.
And then it would be very stable.
Yes, if you can get the things. I think the key thing is to get the stuff down to the right size. You need the commensurability between the lattice.
You have to play in the same scale as the phonons and the quasiparticle electrons in the.
Again, I don't think the phonons are playing that kind of role. I think they're playing a breakdown role. I think the resonance is between the di-electron and the crystal, and of course that becomes less perfect.
It's like I don't think you can say that you have a crystal and you can ignore the photons that do happen due to.
I'm not saying that.
So that those phonons that you can have, they have to go somewhere, and those phonon energies has to be in correlation, in coherence with. But
the phonons exist in all solids, irrespective of whether superconducting.
Yeah, and you have to have some phonons, otherwise it's not gonna vibrate, so it can't even be a temperature.
That's right. I mean, you do have phonons, but whether or not they're relevant to the superconducting thing, I mean, they're in every You know, they're in this computer. There are phonons all over the place. The fact they exist doesn't mean that they have to have a role.
Yeah, but they have to exist.
Yeah, they have to exist. Yes.
So I mean, if you actually
role.
design a topology that has resonance of those phonons, that if they exist, they don't break. They just go in phase, in correlation, in coherence with what the tumble of the photon electron wants to be.
I think such a coherence is important, but I don't think it's necessarily with phonons. I think it's more likely to be with sizes, but
the size shapes the phonons, so it goes together.
True. But the phonons do not need to play a role here.
No, you don't need them, but they end up destroying your correlation of the copper pair.
Always. If you put this thing under a blowtorch, if you take it up to 2000 Kelvin, I'm quite sure you're not going to have any superconductivity, even with very good engineering design.
Yeah. So if you can end up in an experiment and you thought you would have a correlation with a topology, and you ignore the phonons, maybe those phonons will break your experiment, so you don't end up with superconductivity.
That's not for me to do. I'm not going to sit and experiment on.
No,
I'm just going to develop crazy
but it's
theories.
like a problem you cannot just ignore. It will turn up against you if you don't design for it.
You're right. It has some importance. That's right. Anyway, yes, no, phonons could play a role. Anyway, any more questions?
Yeah, about can you have 2D superconductivity? Have you heard about that? I know that you can infringe by neighboring superconductor some superconductivity in a channel that is two-dimensional, but then it goes actually through three-dimensional motion into the two-dimensional plane and then back again.
I think
is that required, or can it exist in a plane only?
Joakim, I want to close you down a little bit on that, because the answer is yes, and in 1D as well. But that's something that I want to keep within Quicycle, not public. And I'm going to put this thing up public, because I think, okay, right. But yes.
Thanks.
You're so welcome. Any more questions?
Yeah, I had one about P-Lab in the Terwilliger experiment. Can you elaborate a little bit about that?
Yeah, I mean, there are a couple of things that matter. This is PT squared, which is the transverse momentum square. So it tells you how hard the thing was hit, how much it comes out sideways. There are other things that matter as well, like the lab energy. You have Q squared, you have X, how hard X is the fraction. There's a dimensionality of the kinematics of these things that include the fraction of the form momentum carried by the struck quark, and that include which affects the center of mass energy of the collision. So there's a plane of possible stuff there, and different physical systems. The zero gradient synchrotron has a particular mass, a particular lab energy. I forget what it was, 12.
So lab energy, is that the spin of the particle due to the rotation in the system, in the lab system?
Was what the spin?
The P-Lab. Is that the energy?
No. P-Lab is momentum in the lab. If you have a different machine, it has a different energy. So you look at different energies. So you're somewhere else on this plane, and you can't get away from that, because
okay, yeah.
The ZGS had a particular energy.
You have a specific
much higher energy. So you're somewhere completely different on the plane. Yeah, and you can't get away from that without redesigning the machine.
Okay. Yeah.
And in fact, the problem is that CERN's really just gone for higher and higher and higher energies. A lot of the interesting stuff's at intermediate energies, but all those machines are, they're not sexy. They're not going to get a Higgs boson out of 12 GeV. So what do? Let's scrap it. So the machines that are really interesting, like the ZGS, just don't exist. And we only have older data. People don't build machines of that energy anymore. Too uninteresting because it's too low energy.
Yeah, we should have some money from the...
Yes,
yeah.
Absolutely crazy. You're not looking at the bits where you could actually do some engineering. You're looking at stuff
but we can at least do it in nanolabs.
Yes.
Some materials.
It might be fun. I'd like to get some money together for a much smaller accelerator, but nonetheless, for somebody else, because I'm not going to do it anymore. I'm going to concentrate on what I do best. So I liked experimenting. Had a lot of fun with experiments, but not for me anymore. Too much work. Any more questions?
And then I just comment, but it's like I'm kind of it's part of my trying to grasp this, because superconductivity is something I thought about a lot earlier, and for me it had a lot to do with the interaction between the electronic and the hole and electron particle interaction for me earlier. Like I imagine, for example, a circulating electron in a two-dimensional electron gas, and its circulating hole going as a pair, forming an Aharon bomb.
Yeah, remember
bomb.
Well, one could build such a system, but remember that in general, in a 2-DEG, one either has electrons or 2DHG, and you can have coupled electron hole things. But the mobility is different in these things as well. So getting to a situation where
maybe that's something that has been a confusion, because actually when you do have a two-dimensional electron gas, you have a Fermi energy inside that two-dimensional electron gas, even though it's completely electronic. The excitations that are above that Fermi level, they are the quasiparticles that you can measure. And the holes that go as valleys or lack of electrons below that, those are the holes that actually could form the Cooper pair. So those are the Cooper pairs as I saw them.
I see what you mean. That's not really... I see what you mean. It is a bit like a Cooper pair. Remember I did the experiment on hot electron spectroscopy as the experiment on electron focusing. So in that stage, we were looking at exactly those things. You do get something which is, so if you take your reference as being the Fermi level, then indeed, when you promote something up which is hot, you also can have something which is cold. So you have hot electrons and cool holes with respect to the Fermi energy. Yes, it's interesting, but that's not what I'm talking about here at the moment. And I don't see, they can be paired as well, but it's more like a sort of electron, it's not like positronium. It's a bit more like positronium, but that's not, anyway.
But I think it's just another way of looking at it. You can either look at it as two electrons moving in opposite time directions, or an electron and a hole moving in the same time direction.
That's true, yeah. But I don't think relevant to superconductivity here. But okay, yeah, no, an interesting discussion as well. Any more questions for anyone else?
I have a couple of general questions. One is, you mentioned the experiment, forgotten the person's name, which couldn't be explained by quarks. And I just wondered to what extent is that a general statement? I mean, is our quark theory challenged by these experiments? Or
no,
are we,
the quark theory is not challenged. The quark theory is good in my view. It's the identification of quarks with the hard bits in a proton that's challenged. It's the quark-parton model which is challenged. The quark symmetry is perfect. It's still there. So it's not the quark symmetry at all. That's beautiful.
All right, sounds good. I just wondered, I've been reading this book. It's called, I don't know if you can see it.
Well, like this one.
You got it.
Yeah. My copy's full of circles and arrows and bits and things like this. I've read it, I think, 3 or 4 times. And actually, Wolf, I'm really grateful for that, because I had a little note to myself that I must mention Carver Mead's fantastic book on collective electrodynamics, because this puts spin central. It's a tremendous book. If you've not got it on your bookshelf, it's not even expensive. So I'd advise you to get one, but it's brilliant and good for you for mentioning it. It's, yes, 100%. Carver Mead does a brilliant job here. He starts with spin and he just takes all the consequences, thinks about it physically. Utterly brilliant. One of my favorite books of all time. So yes, I know all about it.
Right.
Good.
Now I have a third question. Why is mine backwards and yours forward? This is ridiculous. We have the same system. All right. Okay.
I think, Wolf, that means I can't shake hands with you because you're an anti-person.
Yeah. Okay.
Any more questions from anyone else on this one?
I'm thinking that it would be good if these ideas for experiments that you end up thinking about, that you make a list of them and then we can have other people's maybe picking them up.
That experiment I was talking about is already published, I think in the 2019 article. So I put out dozens of experimental tests of this stuff. The high temperature superconductivity stuff is something I want to keep private until I decide what to do with it.
Can you invite Pettersson to talk to you about it?
Yes. No. Joakim, please feel free to contact Per, and yeah, it'd be absolutely tremendous to have him.
But if you leave out the interesting parts from the talk, then it's not as interesting to him, you know.
That's true. But let's just get. Yep. Yeah, Cherry. Sorry. Yep. We'll get in touch with Per. Yeah.
I have one more question.
Yeah,
I have one more question here. I got lots of questions, but I will ask you one more question.
Go on then.
You distinguish between topological binding versus energy binding. I had a concern about that because when I take a deuteron nucleus and then shoot 2.5 MeV photons, I get a neutron out. And I cannot do any other topological things. I just shoot in the energy, supply enough energy to the system, and then the reaction happens and the particle flies.
Yep.
Why should I and how should I distinguish that one from your topological arguments? In fact, that's what I was not able to understand. Because for me, any experiments I do, my energy conditions will tell me what I can expect. And if I don't satisfy the energy conditions, the process doesn't happen. And once it is satisfied, it can happen, right? And I see that in the laboratory.
No, good. So good question.
Why would I go into a different model? Why would I go to a different model than relying upon the energy arguments? That's what I'm asking.
Why? Because there are certain things which don't work on the energy argument alone, like the Tate anomaly. So once you start getting things that just don't make sense with energy, then you need to go into something which is other than energy. I think the reason that you do get neutron production in such a system is that the neutrons got a very high frequency. We're talking about stuff which is 10 to the 23 hertz or so. It's cycling through a lot of different possibilities, and provided the energy is around for, I don't know, 10 to the minus 20 seconds, then it's going to find a way to make use of that energy. So I think the likelihood is very high. I don't think there's much of a bound in terms of the bandwidth of the thing transferring to, in talking electrical engineering terms, to such a system. Okay.
Okay. So there are things which I can't explain by energy.
I'm telling you, I'm no expert on the superconducting side of things. All I remember about superconductivity is stuff I was taught in undergraduate level, and remembering that I didn't really think any of them made any sense. so that's pretty much it.
Talking about superconductivity, helium, superfluidity in helium.
Yeah.
Might be easier to explain, and then from that we can maybe easier talk about superconductivity.
Yeah, you could be right. Yeah, that's a good point, Joakim. You're right. Okay, any more? Okay, well, I suggest we stop the recording, Arnie, and go on to a more general session.